Okay, everyone. So let's keep on moving. So now we're going to be moving into Laplace's equations. I'll let you know that this is not because we saw the Laplacian a whole bunch of times inside of our conservation momentum equation. It's actually because, one, these are the most famous equations in math and physics. So, Bernoulli, famous for arrow. This one's like famous in math physics. So anything that's mixing together math and physics. And you see it everywhere, okay? Absolutely everywhere. So it's in electromagnetism. It's in heat. It's in fluids. And wait a second, speaking of fluid, let's talk about arrows. And what are Laplace's equations? Simply that the Laplacian of a function is equal to 0. And this would be for some function that changes with x, y, and z. Okay. Now, we have developed two big functions that change in the x, y, and z directions. So for us, for fluids, those two functions are the stream function and the velocity potential. And the question is, do our stream function and our velocity potential satisfy Laplace's equation? Because if they do, this is really simple to model. It's way simpler than our conservation momentum equations. So let's figure it out, okay? Let's figure it out. Okay, so what were our assumptions? Well, our main assumptions we're going to be using to do this are the following. And remember that the velocity potential and the stream function don't necessarily have the same assumptions. They don't require all of them. So first off, we're going to be saying that it's inviscid. It's going to be incompressible. And the one we're going to add on now is that it is irrotational. So effectively, that's going to be that our viscosity we're going to say is equal to 0, our density is equal to a constant, and our vorticity is equal to 0. Okay, now with that, let's go ahead and see how this works out. So first off, we'll start with the velocity potential. Okay, and so our velocity potential looked like this. So I get that my u, v, and w, my x, y, and z components of velocity, are equal to the gradient of the velocity potential in those directions. So del velocity potential del x for all of these. And we also know that because I'm incompressible, we can use our continuity equation for conservation equation for mass to get another equation. So this will be 1 right here, and 2 will be coming from conservation of mass. And it comes out to be that del u del x plus del v del y plus del w del z is equal to 0. So we call that one right there number 2. Number 2. I can write it 2 if I want to. Okay, if we plug both of those together, combine them, what we get is our Laplace equation for the velocity potential. So that would be something along the following. Del squared, our velocity potential, del x squared, and we go down the line. Nice. That's what we wanted to see. We could also have written that as the Laplacian of our velocity potential is equal to 0. That's the shorthand version. Beautiful. This one right here is in Cartesian. We could have also written this in cylindrical, the evil way, and it would have looked something like the following. It's not nearly as fun. If you think I'm biased against the, sorry, I forgot to, cylindrical coordinates, you're right. I hated them as a student. I still don't like them now. There are times where it makes things way easier. I do get that, but it's just not fun. Not fun to write. Okay, so we have our Cartesian, we have our cylindrical coordinates here. So that one wasn't too bad. Remember that our velocity potential is 3D. Our stream function, on the other hand, is 2D, which means it's a lot easier to write out. Okay, so now let's do it for the stream function, okay? So we did it for velocity potential. Now for the stream function, we're going to see if this one works. So first off, for our stream function, we know that our stream function, the u component velocity is equal to the gradient of the stream function in the y direction. And our v component is equal to the gradient of the stream function in the x direction. And there's a negative sign there. So we'll call this guy equation 3 because we've got a whole bunch of equations so far. Let's try to keep our numbers together. Now, because the flow is irrotational, that tells us another condition on our velocity components, specifically on the gradient. Okay, so flow is irrotational. And if it's rotational, it means our vorticity is equal to 0. And if our vorticity is equal to 0, we can actually relate together our gradients. And we get something like the following. We get del v, del x, minus del u, del y is equal to 0. This is, just so you know, this would be equal to the vorticity in the z direction. Because it's two-dimensional, we only have one component to the vorticity. Otherwise, if it was three-dimensional, we'd have 3 components. Okay, but getting back to it, we see this right here. And so this can be called equation 4. Now, if I combine these two again, so I'm going to combine once more. Combine this guy and this guy. What do I get? Well, I get my Laplace equation for the stream function. So I get del x of negative of my stream function del x minus del y times the gradient of my stream function with y is equal to 0, or that del squared of my stream function del x squared plus del squared of my stream function del y squared is equal to 0. And once again, I can write that as something like this. That's the shorthand. Okay, so this one right here is 2D. The other one is 3D. Just remember that, don't forget that. So let's put this in red because it's important. For an irrotational, incompressible, okay, for irrotational incompressible flow, both the velocity potential and the stream function will satisfy the Laplace equations. Okay. Great. Why do I care? Well, you actually do care. You care a lot because this is glorious. Okay? This is glorious. For one, Laplace's equation is super popular. That means equations already exist, solutions already exist to a whole bunch of useful problems. The example I like to give is think about a video game. If you've got a video game that's incredibly popular, you can find a walkthrough really easy. You can find solutions. You can find the gamer's guide to beat that video game easy. If you're trying to find some really rare, hardly anybody owns it, it was made in the 1980s, only 2 copies ever existed video game, and you're trying to beat that one, good luck finding somebody who's played it and who cares about it. But for us, solutions already exist for the Laplace equations. So we use these in every case where we can because it makes our calculations a lot simpler. Now the best example of this is for an airfoil. So if I have an airfoil, once again, here's my airfoil. Looks good, like it, nicely done. Okay, and I have a flow going over that airfoil. So I have airfoil going here, I've got air kind of smacking into it, I've got air going underneath it, and I've also got some separation right here. What's separation? Well, it's just where the flow is no longer fully attached. Now, for this airfoil, everywhere where there's nice little streamlines, I can solve the much simpler Laplace equations. So right here I can solve for the velocity potential or the stream function and say, hey, this is equal to 0. This whole area is good for that. And so it's super easy. Now, this region right there, I can't do that. Okay, not here. There, I'm going to need the full equation, okay? Full Navier Stokes equations. But in all these other regions outside of that dangerous place, I have it easy when I'm solving it. And so when I'm doing simulations, it makes things really, really helpful for me. Okay, so Laplace's equation is great for simulations. Okay? It's great for simulations because I can already do a lot of valuable work for it. Beyond that, if I'm doing things experimentally, I'm typically going to be using Bernoulli, okay? Typically going to be using things like Bernoulli. So if I have a wind tunnel that's coming in like this, and I've got some flow lines, I'm trying to figure out, what is the pressure here and here. Well, I can use Bernoulli's for that. That's where experimentalists really shine. And I spelled that wrong. As a note, I can spell my pen's being a little bit slow right now, so that's what's going on here. Okay, Bernoulli is better in that occasion. Another thing is for pitot pressure probes. So if I have a pitot pressure probe, it's a small probe, looks something like this. Put it in a flow, and from it you can measure all kinds of things. And if I look at this guy and I zoom in, not much bigger, what I would see is something along this line. So I would have, my pressure being measured in one place by the airflow going down it, but I would also have a second place where my pressure is being measured, kind of like this. And so I have the fluid flow going down both places, in here and in here. And I can use that to measure velocity. So I'm using Bernoulli's to measure velocity here. There we go. So whether you can use Bernoulli or Laplace, it really depends on are you going simulations or experiment. If you're going experiment, Bernoulli's is usually your go-to person. If you're doing simulations, then you're using Laplace's equations wherever you can because it's way simpler than the full Navier Stokes. And then you just put your hard, more time-intensive calculations for the computer where it actually needs it. Okay, so that's it for this time. Thank you all so much for listening. I'll see you all later. Bye-bye.